Okay, well, thank you again. So I'm going to carry on from kind of where Gabe took us. Again, please, questions, just ask. Don't feel like you're interrupting. Don't feel that, that you're just disturbing me. Don't think, she'll lose her train of thought. I can do that on my own. I don't need any help doing that. So if I say something, it's not the accent, can you just ask me to explain it? Because, you know, we don't want anybody to kind of be lost. You all hopefully in here know each other. Though I was just saying, you know, we're all a community, so kind of make friends, but if you're not comfortable asking the questions, kind of send the emails. Never leave me a voicemail, I'll tell you that. Email's awesome, text is great, voicemail, not so much. But as Gabe was saying, you know, continued education is important. It's also important for us, and we kind of learn from you, and we think about things differently when we interact with you all as well. So we're going to chat about oxidation, reduction, and microbial flaws. Talk about them from a scientific background so you understand what they are, how to recognize them, and how to prevent them from even happening in the first place, right? That's the ideal situation. You don't want to have them in the first place, so that it's not going down the road of remedies and treatments. When you have to treat something, it's expensive. Okay, so we'll look at those mechanisms and prevention. So we'll start with oxidation. Why? Yeah, I don't know. That's where we're going to start. So we'll start off at a basic level. Kind of what is oxidation? If you had to start kind of at the very, very basic level, we'll say it's a chemical reaction where there's an excessive exposure to oxygen or some of these oxidative precursors, some of the enzymes that can lead to oxidation. It's a completely natural process, right? It's not something that is unnatural. It's something that can happen on its own. And we can recognize it from its sensory characteristics. Now, as Gabe was saying, right, sensory is very personal. It's something that, based on our cultural background, it can be very different for each of us based on our experiences. It wasn't really until I moved to the US and we're describing the same thing, but we're using different words, because the apples that I'll have in the UK are very different from the US. You know, the things that we taste, the things that we smell, the words that we use, which is why sensory, we do need to develop that common language. So when I'm thinking about oxidation, the words that I will use is kind of nutty, bruised apple, kind of sherry-like. Gabe was using kind of wet paint. So again, that common language. So as long as we all know what we're talking about, but we can see oxidation, and the rate of oxidation, if you think about, sometimes you cut into an apple or you're having an apple for lunch and you bite into it, and then somebody comes into your office to talk to you and you're like, dang, there goes my lunch. Sometimes it browns really quickly, right? And other times it takes a while for it to brown. You're like, yay, I still have my lunch there. So that's what oxidation is at a super, super basic level. We're all good? If we want to look at a more complex level, a more complicated or more scientific level, we can say that it's a multi-stage reaction, that it's pretty complex. So it's a set of chemical reactions that involves when your juice, so your apple juice or your cider, is exposed to either, and you don't see these kind of very well on the screen, but when it's exposed to the oxygen, and that oxygen is going to interact with some natural components, which they could be either the metal ions, it could be the natural copper or the iron that's in there, and then you've got subsequent reactions with susceptible phenolic compounds. We have phenolic compounds in our apples, right? Different levels depending on the types of apples that we're using. And those will generate what we call reactive oxygen species. And easy way to term them is hydrogen peroxide. Right? Hydrogen peroxide is a reactive oxygen species. And then that will further react to generate these quinones. And it's these quinones that are kind of one of the last steps to things that are browning. So when we've got excess of oxygen, that will go through all these reactions to ultimately lead to what we see as oxidation, which is browning. We should also mention, anybody wants these presentations, just reach out. You're more than welcome to them. Okay, so when we want to manage oxidation, we want to interrupt that reaction, right? We want to interrupt it. So we can interrupt it at multiple stages, and what we would do to interrupt it is we'd use something that we call an antioxidant. Okay, so we interrupt oxidation with an antioxidant. So if we think about what are antioxidants, we could look at them at a basic level, we could look at the tools, or we could look at it at a chemistry level. So we can say that antioxidants at the most basic level are preservatives that keep your cider fresh and bright. They stop it browning, so they stop the colour changing. They keep those aromatics fresh, so they stop the aromatics dulling. They stop it turning into that kind of bruised apple or that sherry, nutty type aromas. We can say that antioxidants are tools that manage oxidative stability, and they preserve the sensory attributes that you wish to preserve. Or if we want to take it a step further, we can say that antioxidants are molecules that are capable of inhibiting the oxidation of other molecules by neutralizing reactive oxygen species and those free radicals, that hydrogen peroxide. So when we're talking about oxidation, depends on how complicated we want to be, right? We can talk about it saying, we just want to keep things bright and fresh. Or we could talk about it at this level. It doesn't matter what level we talk about it at. We're still doing the same thing, right? We're still trying to keep things fresh. We're trying to keep things preserved so that they're not going through this reaction. So how do our antioxidants work, right? Our antioxidants work to stop the oxidation reaction. So oxidation is the loss of electrons. So our antioxidants work by donating those electrons to our unstable species without themselves becoming reactants. So that's how they interrupt that oxidation cascade. So they're giving electrons back into the system so that they stop that reaction happening. So they're like, hey, I'm here. I'm going to interrupt this chemical reaction by giving you something that you were losing, so that we're going to stop the reaction from happening, and we're not going to get that browning from occurring. We're not going to lose those fresh, bright aromatics. So that's what oxidation is, and that's what antioxidants do. So the antioxidants can either work to bind to the metal ions, they could either bind to the oxygen, or they could bind to those reactive oxygen species so you don't get the quinones. So if you're using an antioxidant, when do you think what would be your preference? Do you want it to work at the beginning stage, bind to the oxygen, bind to the metal ions, or at the kind of latter stages? What's your preference? The earlier you stop the reaction, kind of the better it is, right? So when we're talking about oxidation, we want to start talking about it early on. So we want to start talking about working about with antioxidants in the juice, and we want to start talking about things to bind with the oxygen, bind with the metal ions. It's easier to see when you're binding with oxygen because you know that you've got oxygen pickup. Right? This is something that in Australia they're really, really good at, and they really perfected in wine, and then kind of cider has really caught on down under. So if we're looking to bind these different things, we've got different tools to do that, right? It's not the same tool. If I said antioxidants, I gave you 3 different definitions. I says antioxidants can keep things fresh or bright, fresh and bright. I says, or antioxidants are tools. And then I give you the chemical definition. So what are the tools that can keep things fresh and bright? Well, we've got different tools depending on what we're doing. We can use things that bind the metal ions, the things that can bind the copper and that can bind the iron, so that they cannot auto-oxidize, or they cannot participate in what we would call the Fenton reaction. And that could be yeast itself. Yeast will bind metal ions onto their cell surface. So that's the first stage of metal ion uptake. So if we've got an excessive amount of metal ions, they can bind them. We don't generally use yeast, though, as an antioxidant, but they can. We can use inactivated yeast because those specific inactivated yeasts have been perfected for their metal ion binding capacity. We can use specifically oak tannins to bind metal ions. But then you've got to ask yourself, is an oak tannin in line with how I want the final sensory? Right? Because what do oak tannins kind of taste like? No trick questions, I promise. I get fed up listening to myself, which is why I ask you questions. Right? Depending on the level of toasting, depending on how it's been processed, it could be anything from really lightly toasted to very heavily toasted, right? So you have a very light oak influence all the way up to very spicy to really vanilla levels. So you might not want an oak tannin there as your tool. We could look at ascorbic acid, vitamin C. But you've got to be really careful when you use vitamin C. You've got to use it in conjunction with other antioxidants, because it'd be really easy to add too much, and then you kind of go over its protective capability, and then it can work as an actual oxidant. We could use things that bind. I use the word bind just to keep everything the same. It's actually how they can scavenge oxygen. So certain non-Saccharomyces yeast, we have Mechnikolia pulcherrima that can scavenge oxygen to make its own unsaturated fatty acids, so that it can have a really stable and fortified cell membrane. That would be used in the pre-fermentation stage, so in the juice phase, so that you're going to leave that juice deficient of oxygen. Interestingly, it also binds, you can't see it, but the metal ions. We can use certain inactivated yeasts that scavenge the oxygen in the post-fermentation stage, just like healthy lees would scavenge oxygen. They just kind of take them up. Again, you can use your oak tannin. So again, same conversation. Do you want that flavor? But it definitely gives you that option, because tannins are super interesting as oxidants. As antioxidants. Like all tannins are antioxidant. It's just how they work varies because what they bind. And then different things can bind those reactive oxygen species. So you've got different inactivated yeasts. They can scavenge those quinones, those ROSs. So the glutastar has some glutathione, but other specialized peptides that scavenge those susceptible phenolics and keep things really bright and really fresh to take away the oxidation potential. We could also use a different type of tannin. So instead of the oak tannins, we use what we call condensed tannins. So that would be things that are grape-based or even acacia. So acacia doesn't have the same aroma or texture as oak, but it does have the ability to bind your quinones. And this is where SO2 works. So we talk about SO2 as being antioxidant, and we're just like, oh, SO2 is an antioxidant, da 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 da. It's antioxidant and antimicrobial depending on the pH, because when you add your SO2, it's going to dissociate depending on the health of your juice or your cider, the pH, and when it is working as an antioxidant, which is most of it is going to do, it binds to your reactive oxygen species, so it kind of works at the end of that cascade as your antioxidant. So stopping that oxidation cascade, stopping things from oxidizing, you have a lot of options. And traditionally, we use SO2, right? That's the most normal agent that we would use.
So I have a question.
Yeah.
I see no ox on that list. That's something you sell as well. What category is that?
That would be, it scavenges more the metal ions because it is a blend with bentonite and chitosan. Because I forgot. I don't remember all our products. I'm a terrible person. Yeah.
Kind of similarly, early in the process, I was doing some research on like how to maintain color in red juice. And there's some people that say that like a pre-filled passivation with like citric acid forms a protective shield to limit metal ions that interact with the.
Okay.
Is that something that?
So does everyone know what passivation is? So passivation is when you're treating a new tank. You get a new tank, you're treating the tank so that the metal ions are not going to react. So you're kind of neutralizing the surface and you're neutralizing it with an acid. So you really passivate your tank you always do a new tank and you generally do it every 5 years. So that's not going to help. It's just a treatment for a new tank. So red fruit, you would protect color. We can protect color in very similar ways, but to best protect color, it's your anthocyanin, tannin, polysaccharide binding. That's kind of the trifecta. So we would want to put in a polysaccharide as well, which would be your inactivated yeast, which would have the most reactive polysaccharides. So we'd look at something like OptiRed in that case. We could chat about that on the side. So oxidation, why is prevention a goal? And this is kind of where the context comes in, right? Well, if your goal is to retain these really bright colors, then you want to protect from oxidation. Is it to maintain your fresh, clean aromas if that's the style of cider you're making? The other way is if you're looking for canning or for early consumption. Well, when you're canning, you all know that you need to keep your SO2 low so you don't get your canning taint, right? So then you're looking for other ways to protect from oxidation. So then that is kind of some things to think about why you want to keep from oxidation. But sometimes when we're talking about it, like Gabe was saying, some of you are saying, I like a little bit of oxidation. So is it ever a good thing? Well, again, depends on what you're making. So sometimes in some traditional styles, well, it helps develop flavors. Sometimes when you have a little bit of oxidation in there, you have a little bit of those nutty flavors, a little bit of those sherry notes, which can give you kind of some of that complexity there for a very specific style of beverage that you're producing. It can also, I don't know if you noticed when you were tasting, because those samples, we did get food safe samples so you can smell and taste. I don't know if you noticed a difference in the mouthfeel. So with the acetaldehyde one, the mouthfeel was a little softer. So you can kind of soften things up with the oxidation because you're softening up some of those tannins as well, and you're integrating things. So when you're doing a barrel aged style, a little bit of oxidation does help. Helps with the bridging of the tannins so that you don't have as much tannins interacting with the salivary proteins in your mouth, so it's not as aggressive. And you can introduce some of those other aromatics as well. Or it gives you a blending option, right? Just a little bit of complexity to some of those highly acidic ciders that you make. So it could be a good thing. However, the key is control, right? Because a little bit is good, a lot can be bad. So it's a balancing act. And it's only you that knows what a little is and what a lot is, right? It's not something that I can tell you. This many milligrams per liter is what you're aiming for, because it's all based on the entire chemistry. It's based on your final style. It's based on the shelf life. It's based on the consumer. It's based on the market. So that's why, like with numbers, I'm not going to say, you should aim for this with acetaldehyde and oxidation precursors, because again, a little bit could be good based on the style. But if you go too far, it's hard to get back, but you can get back. It's easy enough for us to kind of get back with some little bit of management. We can get back with using certain tannins, as I said. You can get back with your chitosans. You can get back there with proper SO2 management. But again, best not to let it get that far. So reduction. When we say reduction, Gabe was asking, okay, what do you think about reduction? Is it ever a good thing? Generally, it's not something anybody ever is going for. So again, at a basic level, reduction refers to a chemical condition where there's limited exposure to oxygen. So we could think about that as being the opposite of oxidation, right? If oxidation is excessive oxygen, reduction could be limited oxygen. Limited oxygen could be a good thing, right? Because it protects stability. It protects your color, it protects your aromas from being oxidized, and as we'll get to talk about, it protects from microbial flaws. But too much limitation is going to give us our other challenges, right? So it's kind of like a teeter-totter or a seesaw, right? You don't want not enough, because then it goes one way, but too much, it goes the other way. So oxygen management is really important through the entire production. So that is what reduction is at a very basic level. You've got limited exposure to oxygen. From a more chemical standpoint or a chemical definition, if oxidation is loss of electrons, reduction is the gain of electrons that results in a decrease in the oxidation state. And it's this decrease in the oxidation state that results in the formation of volatile sulfur compounds. And these are formed from different sulfur sources in the fruit. And as Gabe was talking about, a lot of that is due to yeast stress. We'll call them reductive compounds, reduced compounds, volatile sulfur compounds, sulfur-like off odors. Kind of call them lots of different things. I normally just write VSCs because I'm lazy. You call them what makes sense to you, but a lot of them are. We're generally using different nomenclature for the same thing. So when we're talking about these reductive compounds, these VSCs, these SLOs, the sensory identification, so if acetaldehyde and oxidation is sherry, bruised apple, wet paint, these reductive compounds, these sulfides, mercaptans, disulfides, I never pick it up as rotten egg. I normally always pick up hydrogen sulfide as being more skunky. But different people, again, different things. But when we get into our mercaptans, these are more the kind of burnt aromas, your burnt match, your burnt rubber. Once you're getting into your disulfide, so disulfide, whether it's an ethyl or a methyl, it's when you're getting into your rubber, your canned corn, your asparagus, your kind of cooked vegetables. And then kind of none of these are very pleasant. Those are generally not the aroma compounds you're trying to get in your cider. I've never had anybody call me and say, hey Nichola, can you help me make a cider? And I'm really going for asparagus with a side of cooked corn, right? Generally doesn't happen. So they're all like, hey Nichola, I want to have something that's kind of more white flour with a side of, I don't know, passion fruit, right? These are normally not the things that they're going for. And you'll see the sensory threshold is in the parts per billion level. So at very, very low levels, they can kind of overtake all your positive aromatics. So how do we get all these different compounds? How do we get hydrogen sulfide and some of these other volatile sulfur compounds? Well, H2S, that's kind of the main compound. It is generally formed via yeast stress. So you stress your yeast, you make your yeast unhappy, they're going to let you know, right? It's not a little warning. It's not just like, hey guys, I'm not very happy. It's like, hey guys, I am really mad at you right now, right? It's not just a little wave. It's a screaming shout at you. And then when H2S reacts with other compounds, that is when they're going to form generally your mercaptans. And the mercaptans are formed when your H2S reacts with an alcohol, so that could be ethanol, it could be methanol, it could be butanol, or they react with a carbon. Your mercaptans can go to disulfides. So once your mercaptans are oxidized, that's when you get your disulfides, and that mercaptan disulfide can kind of shift back and forth. H2S, I'm going to say relatively easy to treat. Mercaptans and disulfides are really difficult to treat, so we don't want any of them, but if we have H2S, we want to get on it straight away so that we've got the easiest thing to manage possible. So we don't want this, we don't want this, and we definitely don't want these, because once we start shifting our sulfides into our higher sulfides, things become really, really challenging. So what are the precursors for our H2S, right? Where do these sulfur compounds come from? Well, there could be from sulfate, SO4 2-. You don't really have that much sulfate in apples, but when you start blending in other things, you can really increase your sulfate source. But you can have it from different agrochemical inputs into your orchards. It could come from your sulfur-containing amino acids, from your cysteine and your methionine. You do have enough cysteine in your apples, and you do have enough methionine, and it can come from SO2. So your sulfate has a really high oxidation state, and remember, in chemistry, everything kind of wants to be stable. It's going to find friends to make it stable. So it's going to find friends to like make itself into a neutralish state. So it's you're going to have your sulfate is going to go to sulfide, and it's going to go to hydrogen sulfide. So sulfite to sulfate, to ite to ide. So you're going to get from sulfate. Your sulfur-containing amino acids, you're going to have your cysteine, which can be broken down to hydrogen sulfide, your methionine, which can go directly to mercaptans and DMS. Your SO2, so SO2, when we say SO2 in this case, we're talking when you add a potassium metabisulfide and it dissociates into the different forms based on pH. So I'm saying molecular SO2, so I'm actually talking about SO2, which is uncharged. So molecular SO2 is the active or the antimicrobial form. and it's taken up by the yeast, and the internal of the yeast is like kind of internal of your mouth, which Gabe was saying with mousy, different pH. So the inside the yeast is about pH 5.6. So what happens, that SO2 that's not charged dissociates and gets a charge on it, and it becomes bisulfite. So again, it's going to further break down, and you're going to go to your sulfite, and then you're going to go to your H2S. So your yeast is going to find ways to get it down to that H2S when it's stressed. Okay, it's going to find a way to detoxify these sulfur-based compounds when it's stressed from these different precursors. So when we talk about managing these compounds, there's not much we can do about sulfate, sulfur-containing amino acids. We'll talk about good nutrition. SO2, we'll talk about proper SO2 management. Okay, so these impactful factors. So your juice and pre-ferm practices, how do we positively impact those so they don't go to H2S? Okay, well, if you have high SO2 or other precursors, what does that mean? That can go to H2S, right? So we want to minimize our beginning SO2 levels. You'll see in a few slides, I'll tell you that if you add more than 80 parts SO2, that can go to H2S. So we want to have our SO2 add based on the health of your fruit, health of your juice, and your pH. Your clarification level, right? You need some yeast. You need some yeast for your solids to stay up. You need some solids for your yeast to stay in suspension, right? So if and again, this is a teeter-totter. So when the juice is too clear, the yeast don't have all their solids that act like little life rafts to keep them in suspension. They get stressed out. Stressed yeast or unhappy yeast. But when there's too many solids, they're unhappy with you as well. Therefore, guess what they do? They get stressed. So again, we'll talk about clarification levels in a couple of slides, but you want to aim for 1 to 2% solids. Solid levels also linked with aromatics. There's a few people that when they're new to cider, they don't realize that clarification is important. They just get their juice, press their juice, and go straight to ferment and miss out that very important step in between. If you've got a high level of contaminating flora, or you have a long time between juicing and active fermentation, well, that contaminating microflora will utilize a lot of the vitamins and minerals that's essential for healthy fermentation. If you don't have all those vitamins and minerals there, particularly your thiamine, your calcium pantothenate, which are essential to help the yeast break down the sulfur compounds to their end point, the yeast will stop at H2S, and that will be kicked out of the cell. So again, having as healthy fruit as you can, or using appropriate antimicrobials. So there's a lot of things you could do in the pre-fermentation phase to minimize H2S production. Your fermentation practices. This is super important to get right. So I just said your vitamin deficiencies. So your yeast need vitamins just like we do, which mine's is still sitting in my purse over in the corner, not the best. But they need inositol, biotin, thiamine, calcium pantothenate, folic acid, and riboflavin. So they need those 6 B complex vitamins. the vitamins are growth factors for the yeast. So they're essential for a lot of the metabolic activities. And we know that when we don't have enough calcium pantothenate, and we know that when we don't have enough thiamine, and we know when we don't have enough biotin, that our H2S levels are elevated. So ensuring we have those vitamin levels up there is super important. Your yeast also need a proper balance of nitrogen. Apple juice doesn't have a proper balance of all the amino acids. So there's 20 amino acids with a genetic code. Yeast can use 19 of them in a fermentative environment. So they can use everything except for proline. So if you're unbalancing your nitrogen, they're going to use all the early assimilable amino acids first, which is mainly what's in your apple juice. So they're going to run out of nitrogen super quickly. And so even if you're running your yarn, they're going to like, thanks so very much. I used all those within the first 2 to 3 bricks, or the first 20 to 30% sugar, and now I'm starved, right? So making sure that you are looking at your yarn and have a proper feeding schedule is so important. It's becoming more talked about, which is terrible grammar, apologies mother, to just open your pack of yeast and throw the yeast in there. It's nice and easy, let's just do it. You do you, right? But if you think when you get your yeast, it's in an active dried form, 92% of the water's been removed to give it longevity, so gives it shelf life. You want to make sure you replace that cellular water with proper water, preferably in one of your GoFirm products, to get all those vitamins back in there as well as the minerals. But make sure you rehydrate your yeast. When you add it, mix it in. When people like to add their yeast just right in the top corner, and they're like, oh, but it's self-mixing. And I'm like, no, it's not. And I recently explained it to somebody. I'm like, well, it's like your yeast. It's kind of, you stick it on the top corner. It's like that beautiful apartment complex, which I've been admiring the rooftop garden over there. I don't know, say 500 people can live in it, right? Throughout the entire apartment block, there's enough different resources for 500 people, right? Say if there was 500 people all living on that top roof garden, would they all fit? Is there enough resources right on the top for all 500 people? How long until somebody got thrown off, right? So, but there's enough resources on every single floor for them all. So it's the same as your yeast in the tank. You got to give them their own space. When they have their own space, they've got access to their own nutrients, they've got their own little kind of apartment, let's say. So just kind of mix them in and make sure the temperature's appropriate. I will hear all types of people who are making all types of fermented beverages saying, I like my ferments to be cold, I like my yeast to be struggling. And I'm like, okay, I'm going to drop you off in Siberia with no coats. Why, right? When they struggle, they're never going to perform as intended. So if you want a cold ferment, choose a strain that can actually ferment at the temperature that you want it to. When you get your yeast, and you read all the things it can do, that is what its genetic potential is. And when you use it out with its recommended, it's not going to perform and give you those things. So just respect the temperature. The yeasts are all different genetically. We understand its sulfate assimilation pathway really well, sulfur, how it can break down SO2 really well. We understand its sulfur amino acid biosynthesis pathways. So we know where those are contained on the yeast genome. Some yeasts have the tendency to produce more H2S than others. So if you're continually struggling with H2S, production, you're doing everything correct. There are other strain options for you. Lees compaction, make sure you're keeping your lees suspended as well. So there's a lot of things that can impact how much volatile sulfur compounds you get. So are they ever positive? Yeah.
Is there a certain phase in the yeast, like, that you would recommend where mixing is more important? You know, like, is it prior to logarithmic growth? Is it during stagnation? You know, like,
So if you had to choose, it'd be at the beginning of ferm and at the end of ferm. So during fermentation, it will kind of mix because CO2 generation, but it depends on the size and shape of your tank. If you're in a tall, skinny tank, you should constantly mix, at least once a day. If you're in a short, fat tank with the convection currents, it should mix during fermentation. If you're not mixing at all, it takes about 7 days for the metabolites to be the same at the top of the tank and the bottom of the tank. Mixing's your friend. Cheap and easy. So are volatile sulfur compounds ever positive? If somebody can prove to me that you do get thiols in apples, we'll say yes. You can definitely get ciders that taste of passion fruit, of guava, which can be thiols, but I can't find any actual research papers that say that. So there are sulfur compounds that are positive, but generally the ones I'm discussing are negative. So I would say at this point, no, we don't want rotten eggs. So again, prevention. Limit your SO2 additions to less than 80 ppm. Manage your clarification levels. Less than 120 NTUs, 1 to 2% solids will give you nice fruity flavors. Proper yeast handling, rehydrate, attemperate and mix. If you don't have proper hot water, if you don't have 100-degree water, then look at using GoFerm Sterile Flash that allows you to rehydrate your yeast at 65 degrees. Appropriate yeast nutrition. Make sure you get your vitamins and minerals in there with your rehydration nutrients. Make sure you're looking at your nitrogen, having a good balance. And make sure you're managing temperature, mixing, and take care with aeration. And this is why I always mention take care with aeration. Yes, ma'am?
Just one quick, you said if you don't have access to hot water, you could use
GoFerm Sterile Flash. So that's the new rehydration nutrient. It's microagglomerated and it's very, very high in sterols. So it allows you to bypass hot water rehydration. Pretty cool. Yeah. So this is why I'm fearful of splash racking when you have sulfides. So you've got sulfides, you've got your methyl mercaptan, you add oxygen, remember it's an excess of oxygen, you get your disulfides. Well, if you look at your threshold, 1.5 ppb, with your methyl mercaptan, which is your burnt match, rotten cabbage. Your threshold for your DMDS is 10 ppb. So what you can do is turn it from something you can smell to something that you can't smell. So it may very well still be there, just you can't smell it. And once it reduces back, it can show its ugly face again. So I'm always a little bit wary with splash racking, so I always just like to mention that. Okay. Time in a H2S formation real quick. If you see it early during fermentation, it's generally a nutrient shortage. If you see it late ferm, it's generally through just super stressed yeast, super stressed ferments. You've had it too cold, you've not been mixing your ferments. Post-ferm, your yeast are all compacted into your lees. Once they're more than 1 mil in your lees, then they're getting stressed out. If you see it in the packaging, I really don't think anybody goes to pack with knowing they've got sulfides. And I think that's when they've oxidized it and it's reduced back in the package. So that's kind of when I see That would be your kind of shorthand. So remember, your mercaptans and higher sulfides are going to appear after H2S. And that's when you'll generally see them from mid-ferm onwards. You generally don't see them late. So prevention, post-ferm, get off your gross lees and try to keep stirring your lees and have good racking practices, because you don't want your yeast trapped in those lees. Trapped lees are going to be stinky lees. And what you treat with depends on when you're seeing the volatile sulfur compounds. So early, again, correct nutrients, making sure your vitamins are there. I don't understand why, but your tarotannins, your FT Blanc can work to bind reduction. We use tirage tannins when we go to method champenois. Keep your yeast in suspension. Late fermentation, you can look at your regulus, which is your yeast with copper on the cell wall. Post-fermentation, include your tannins, your copper, your bentonite, your regulus, your NOx, which I forgot about again, because apparently, you know, it's not forefront, don't tell Lee, and your racking. So there's a lot of things you could look at. And then microbial flaws. Then I'll go through this and then I'll hand to Nate. So microbial dynamics starts in the orchard, right? And the microbiology is going to be heavily influenced by the environment and the environmental factor. So the variety that you're growing, the climate, the agricultural practices, the actual apple chemistry, and your inputs. Your inputs have a huge impact on the microbiology. But what we really see is what changes from pre-ferm on. That's what has the biggest impact on the microbiology. So pre-fermentation, that's when we see the non-Saccharomyces really taken off, and then that will kind of die down once fermentation starts and your Saccharomyces taking over. Your acetic acid bacteria, we start to see that pre-fermentation, it dies off during fermentation and it can take off again post-ferm. Your lactic acid bacteria is kind of pretty low during the early stages of fermentation. During a struggling fermentation, it can kind of start to take off, and uncontrolled, it can play a role again during this aging and storing. So your goal is to really get into this active para-alcoholic fermentation as quickly as you can. If you choose to go through malolactic fermentation, which some people said that they do, and past this stage, you want to make sure that these organisms are in control so that you're not encountering any flaws. So in the fruit phase, what organisms? I just said it's a lot of the non-sac. These are your oxidative organisms. These non or very mildly fermentative organisms. So we'd say collectively they're non-Saccharomyces. If we're talking about the genus that are there, it's the Hansenísporas, Candidas, Lactantias, blah, blah. But we can also find Brettanomyces in the fruit phase, especially on damaged fruit. And we can find the acetic acid bacteria as well, both Acidobacter, Gluconiobacter. How do we control those? Well, generally through diligent antimicrobial agent use. We're generally going to use SO2. So again, SO2 is antimicrobial and it's antioxidant, which is kind of why it's been our very traditional product to use. But again, you've got to be diligent because it is linked to H2S production. Cellular hygiene is so important. We want to make sure that in the juice phase, it's very microbiologically delicate, so we want to make sure that it doesn't get contaminated. And a lot of the newer tools are really interesting in the pre-ferm phase, kind of the chitoxans, the antimicrobial specific chitoxans, not the antioxidant chirosans. They're very different in their formulation. And some of our non-SAC. So I mentioned Nichola as an antioxidant because it scavenges oxygen and metal ions, but it also takes over the ecological niche, which is why it can work as an antimicrobial agent. And the fruit phase organisms require a lot of oxygen, so you want to try and get onto fermentation as quickly as you can. Because a lot of the flaws, or the major flaw I think is yeast-based at this time. It's generally the ethyl acetate. So that's kind of what we see mainly at this point, or that would be the majority. Fermentation phase, what is generally conducting the fermentation is Saccharomyces species, but we can also use Torulaspora delbrueckii to conduct the fermentation. Torula can go 6 to 8% alcohol, so that's something new to play with. To ferment to dryness if you're going to kind of that alcohol level. And bacteria, lactic acid bacteria, depends if you want to see it there or not. Our microbial control options, well, we want to have good fermentation practices, right? So our ferments don't stick. To control our bacteria, generally, as I said, our lactic acid or gram-positive bacteria. So again, we're looking at our chirosans. Generally, our alines are bacillus, our lysozyme. Again, you can add a little bit of SO2 during an active ferment. When I say a little bit, it's 10 to 20 parts. pH dependent, doesn't impact our yeast. Our microbial flaws that we'll generally see during ferment is going to be diacetyl lactic acid, and if you let it go too far, can also be acetic acid.
Did you say you could add SO2 during a fermentation?
You 10 to 20 parts, pH dependent. If you see your VA number creeping and your malic dropping because of bacteria, it doesn't impact your yeast as long as your yeast is pretty strong. Yeah.
I thought that caused, what's the nail polish thing?
Ethyl acetate. SO2, no. Yeah, just a tab. Post-ferment. This is where we really focus on our microbial dynamics, because a lot of people think, well, I'm safe. I've got rid of my fructose, right? I'm good. This is where all the funky things happen. Super funky. The higher the pH, the higher the risk. So this is where Brettanomyces can be a pain, and I'll explain why it can be a pain. Your bacteria, lactics, acetics, and yours, and I struggle over Zymomonas, can all be challenged. So you've got your gram-positives, your gram-negatives. The lactic acid bacteria, so you've got your Enococcus, I split out your lactics into homo and heterofermentative. So that is ones that can produce VA from sugar or not VA from sugar. So if it's homofermentative, it cannot, versus heterofermentative that can. So Brettanomyces. Brettanomyces is a challenge for us still. There's 4 major genetic groups of Brettanomyces, and they correlate with their ability to produce volatile phenols, so the 4EP, 4EG, with its ecological niche. So where we find them, are they found in the biofuel environment, in the winery, the brewery, or the cidery? You guys are in your own ecological niche. I'm sure you really don't want to be in this case. And their SO2 resistance. We will, as I said, find them in the orchard, specifically on damaged fruit. They are present in really low levels though. And we do need microbiological, molecular microtools to detect it, because they can go into what we call a viable but non-culturable state. And so when we plate them, they don't show up on plating. It's like they go into a comatose state, and we're not going to be able to pick them up. But through genetic tools, we could pick them up because their DNA is still there. But generally, we're going to pick them up through the maturation phase in the cidery. And because some strains confer this SO2 resistance, that's why we need to look for new tools. This has been a big research part of academia in the past few years, because some strains of Brett are diploid, some are triploid, and they're thinking that could be related to the SO2 resistance. But SO2 can transfer over the yeast cell wall membrane, because as I said, molecular SO2, which is your antimicrobial fraction, is not charged, and the Bretts that are resistant, like, hey, thanks very much, and just kicks it back out. We're like, well, that didn't do much work. So because when we look genetically, we're like, oh, you have Brettanomyces bruxellensis, and we're no further, right? That's all we know. And the challenge is, and we can't see our little arrow here, but this is our Brettanomyces sensory wheel. So when we look, we know genetically we have Brettanomyces, or we might know down the microscope we have Brettanomyces, but we don't know who we have. We don't know what strain. And some strains are beautiful, they're fruity and floral. Some could be woody and spicy, other earthy, savory. Then you get into the animal and rotten putrid. And that's where you're taking the gamble. So that's where you need to assume the risk. If you're going to call us and you're going to say, I have Brett, what do I do? As microbiologists, we're going to say, well, that is a spoilage organism. But if you so happen to have an in-house strain that produces, I don't know, violet, and you love it, that's fantastic. If you have something that produces tropical fruit, good on you, right? But if you have a neighbor down the street that has Brett and it's fecal, we're talking the same organism, right? This is where strains are really important to understand. So again, Brettanomyces is difficult, which is why we're always going to talk about it as being a spoilage organism until we understand it better at a strain level. So early detection and control is the key. So we're going to detect it genetically. So we have to manage it in the cellar through temperature, pH, hygiene, and O2. It's quite easy to manage. It's as if you manage your O2s and you manage your temperatures, you can kind of keep it at bay, because it does like to be in an oxygen environment. Maintain molecular SO2, so maintaining generally a 0.8 molecular is good. Now, if you've got a SO2 resistant strain, that's a little bit more difficult. You need to do your monthly analysis. So VA, most strains of Brett will produce acetic acid, but most spoilage organisms produce VA, which is why we want to be measuring it. Make sure your SO2s are in check, and your newer chitosanes can be used to inhibit Brett. Treating it, your chitosanes, your Velcro filtration. If you have negative sensory, then that's when you're looking at reverse osmosis to remove the most offending phenolic compounds. But bacteria, this is kind of what freaks me out most. I haven't heard this so much in the cider industry, but I hear it in the wine industry a lot. People will get their scorpions and they'll send it to me and they'll be like, hey, Nichola, can you look at my Brett numbers? And I'm like, oh, your Brett's good, but look at your lactobacillus. And they're like, oh, I don't care about that. I'm like, okay, I will freak out for you. Because their lactobacillus numbers, their lactobacillus casei can be off the roof. Their kunkiae can be like down the road and around the corner. So they've got some really huge bacteria numbers, but we've just been trained to think Brett is the only bad guy in our wine. You guys are been thinking, oh, the only bad thing in my cider could be Brett. And unfortunately, we're not seeing the true extent on this projector. But you have got so many different potential sources in your cider that, given the opportunity, can lead to spoilage. So for spoilage to occur, you need to have the substrate there. So in this case, we can have ethanol, we can have glycerol, we could have fructose, we could have citric acid, we could have pyruvate, we could have amino acids, malic acid, what have you, right? So just because you've got no fructose left doesn't mean to say you don't have other things. So you've got to have the substrate there. You have to have the organism there, and you have to have the conditions conducive to growth for that organism. So if you have those things there, you have the potential for spoilage. So if you take away their ability to grow and metabolize, it's okay if you have the substrates there. Because Enococcus, given the substrates, given the conditions conducive to growth, given their genetic ability, can produce biogenic amines, so things like histamine, putrescine, cadaverine, tyramine. You know, I mean, cadaverine just sounds great, right? Putrescine just sounds great. Mannitol, which is kind of a weird texture. Diacetyl, geraniol, which is like crushed geranium leaves. The geraniol's kind of over here. So if you add sorbic acid, so that's an additive with ethanol, lactic, acetic, and kind of mousy. You can kind of see them all there. The good thing with Enococcus, at least our Enococcus, they don't have the decarboxylase enzymes to produce biogenic amines. So you've got a lot of other things in there that can lead to different flaws in your cider. So that's why we say their potential impact. So just know that they're there. So knowing which lactic acid bacteria you have is important. So knowing the genus and species that are there. So you can say, oh, I have Enococcus and I have this chemical, so I need to control my Enococcus, or I have Lactobacillus kunki, therefore. But using just general broad spectrum, good cellar hygiene, you're going to protect from a lot of things. So again, temperature, pH, good cellar hygiene, topping, treating, O2 management, maintaining 0.5 molecular for lactics is good enough. Good monthly analysis, good inhibition management. So with lactics, you can use lysozyme. Can't use it for Brett, can't use it for acetics, but you can use it for lactics. Okay, so treating, again, very similar to treating for Brett. Acetics, pretty much the same thing, except for we're not going to use lysozyme. If you have a lot of aldehydes from your acetic acid bacteria, your tannins can bind aldehydes. They're not going to remove the bacteria, but they can kind of mitigate some of that effect. So again, acetics are pretty easy to control and manage when vigilant. So just know, not to scare you, but there's all these things, so just think about it. It's not realistic to have a microbial-free cider, so that's why we talk about microbial control. We talk about broad spectrum treatments, but we can have very targeted treatments when needed. And talk about risk management, just be aware, right? Knowledge is power, because controlling microbes is going to help you preserve quality. So we have all these different options to use at different times depending on what's needed. We also need to understand that we have things that are microstatic and things that are microcidal. So microstatic things will just keep the population in check, and microcidal things will kill it. So you just know what's what. And I'm going to kind of turn it over to Nate, and he's kind of going to talk about how you can use things and how you can use what we call this thing called hurdle technology. And that's the implementation of different tools, whether it's different chemical, biological, so that your things are free from spoilage organism by combining these things so that you're using the right, so that you can use the right tool so that you're not, get this in the right way, so that when you're using the right tool at the wrong time, so you're not ineffective, right? You want to be using the right thing at the right time and making sure that kind of everything is being taken into consideration. So I'm going to give it to Nate, and he's going to be talking about making your cider stable.